to start out, so the actual design that we use, or the website that we use, is called Agilent Shore Design, right? So if you just type in Agilent Shore Design into Google, it'll basically come up with this website. So this is the website that we use, Agilent Shore Design. It's called Agilent eArray. So I'm going to click that. And then basically it has like a username and login. So you would just have to register a username to use the actual website. So I have mine here. So I'm going to click in, and so I'll sign in. So this is the portal that you can basically design all of Agilent's custom products. So if you want to do custom fish, chip, basically anything you want to design custom, you would do through this website. So the main reason we use it is to design aCGH arrays, right? And so you can see kind of just designing, we have everything that you can design here, designs in progress. So these are ones that I've been working on or just testing out. It then has basically the recent and favorite. So this is designs that you finalized. So what we want to do is basically go to create design and then do aCGH. I click that. So then it'll give you a couple of different options. We can do standard, advanced, create design, create probe group. So we're going to start with just a standard, and we're going to do create design. I'll explain probe group in a little bit, but I think it's good to start out with the easiest. So we're going to say here a standard design, create design, and then we're going to hit confirm. So then it brings up this design website. So the one thing we put is the design name. So this could be anything. So I usually try to name it descriptive for the chromosome that I'm targeting. So let's say I'm targeting chromosome 4 and chromosome 10. I can just put anything. So for this, I put chromosome 4 and 10. So the build, we always still use HG19, but we can use HG38 if we eventually want to switch. But for the time being, we use HG19 for everything. Application is going to be aCGH. So the array format here, so this is the important first, I guess, choice that you have. And that is how many samples do you want to fit on that particular array? And so effectively, the price of an array is the exact same. And so it's a trade-off of you can fit either more samples on the array, but you would have less probes, or you would fit less samples and have more probes. And so your four choices are effectively an 8 by 60K. So that means you can fit 8 samples on the array, and there are 60,000 probes. 4 by 180, so that's 4 samples with 180,000 probes, 2 samples with 400,000 probes, or a single sample on an array with 1 million probes. So that 1 by 1 million, that's the highest density you can get for an individual sample. So you should also think that we can strip these arrays and use them again. And so you have to think about how many samples you want to run, and also that you'll be able to strip the array and use it one more time. And so if I were using this 8 by 60K array, and I were to order one array, I could run 16 samples on that array. And so that's totally a choice by the user. You would never really use these down here because the price is the same. And so we would always want a higher density array. So this is 8 by 15K, which is the old, kind of the old version. And this is the higher density. So you would always choose one of these 4 options. And it's really just depending on how many samples you want and the density of the array that you're trying to pick. But for the time being, let's just say 4 by 180K array. And so then that basically picks everything here. So we're going to hit next. And definitely just stop me if you have any questions or concerns. So now we're basically defining the targets that we wanted to pick, right? So we have on this left-hand side our array design. So it's showing our name, our species, which is going to be human, format, and then it has this target region and probes. And so right now you can see the probes, we have a lot of information not filled in yet because we haven't put anything in, but you can see that there are some probes that are showed. So one is control probes, and this one is the percent filled. So this percent filled is saying out of the 180,000 probes available on this array, this is how much it currently has already filled up before we put anything in there. And what that is basically filled from partly is this genome-wide backbone. And so that is, no matter what array you're designing, you're always going to have a backbone, which basically means that although you may just be targeting chromosome 4, or you just may be targeting the short arm of chromosome 2, you'll still have some probes that fill the entire genome. And so that just gives you like a backbone to visualize, to make sure everything worked correctly, to make sure there's no other chromosomal abnormalities. And it really just helps you make sure things look correct besides
like
the region that you're looking at.
probes?
Yep, go ahead.
Like it's like a control probes. So you are looking at other chromosomes, like if they are.
Yeah, so it's basically probes that are totally unrelated to what we design.
Okay. This is
so they're
something
just
control, like compare.
Yep, yeah. So kind of a comparison just to make sure the rest of the genome. So all of this you would effectively leave the same. And so the targets here, so that is, and you can see it's giving a lot of different examples of what we can put in here. So that is saying, what do we want to target, right? And so for this, we want to go to the genome browser, and we'll make sure we're at HG19 here. And so right now, so we're sitting at chromosome 4 right here. So it really depends on what we want to do. Let's say we just want to target chromosome 4, right? So I'm going to just put CHR4. And so what UCSC is going to do is saying, this is, once it loads, so it's saying chromosome 4 is at base pair position 1 through 191 million, effectively. And so, and you can see here, it's basically highlighting the entire chromosome. So let's say I just wanted a chromosome 4 array, right? I can copy this. That's saying chromosome 4, position 1 through 191 million. So I can copy that and I can put that into here. And I can say next. And so what that's saying is that effectively, it's going to target just this chromosome 4 position at a 191 million bases, right? And so you can see here, it's giving us some metrics to say if it were to just fill this 180,000 probes with this 191 million bases, the average probe spacing would be about 1,100 bases. So that basically means that every about 1,000 bases, it would be able to fit a probe onto the array. But let's say we wanted more than just chromosome 4 on this array. Let's say we also wanted chromosome 10. So one other thing to think about when you're designing arrays is the reusability, right? So although if this is like for that translocation that you're looking at, where you may just want to target 4q and 10p, you may want to just target the whole chromosome. So if someone ever needs a chromosome 4 array, you would just have it already available. So you want to just watch that you don't design something so specific that you'll never be able to use it again. Sometimes you do need to do that, but I try to design probes that are a little bit more liberal in that you can use them again for different projects. And so you can see, go ahead.
So you are recommending not to like just this specific for this translocation, design a primer for this translocation, Just design
Yeah,
whole chromosome 4 and chromosome 10, and we can use any other experiment.
I
Okay.
would typically recommend that. Um, and there, I mean, it depends. It's all like this balancing act because you want it specific enough that you'll be able to do what you want with the probe, but you don't want it so specific that you'll use it once and then it's like not something you could ever use again for another project. So it's kind of this like balancing act where you need to make sure the coverage is dense enough that it's usable for you, but not so dense that it's like concentrated in a region that's only good for one patient. So let's say, so basically right now, I have it targeting the entire chromosome 4 and the entire chromosome 10. And remember, this is on 180,000 probes. So I'm going to hit next. Right, so now it's saying it's targeting chromosome 10 and chromosome 4 with the average probe spacing of about 2,000 bases. Right, so that is basically saying that across both, so if you were to run this array, you would have coverage of the entire length of chromosome 10 and the entire length of chromosome 4 with an average probe spacing of about 2,000 bases, which is pretty good. It's about what you would need to get a breakpoint junction. So obviously, the more dense,
Sorry,
better.
Chris. For the breakpoint junction, is there any cut length for, like you say that 2,000 is like will be okay. Is there any cutoff for that to find the breakpoint?
I
Like
mean,
any
then
pause there?
yeah, it starts to become somewhat like subjective because it's like technically, it's like you could always like keep trying primers and keep working in. So even if it was a 10,000 bases difference, you could still get the breakpoint junction eventually. Yeah, I would say at like 500 bases, it's the easiest, and it just gets a little bit harder from there. But 500 bases is very dense and wouldn't necessarily be an array that you'd be able to use again for something else. But between 1,000 and 2,000 bases average spacing, I think is the easiest to do. So, and it was 4 and 10 was the translocation, right? I think for that sample, I can't remember. But anyway, so let's say I want to target that, but let's say I can go back here and let's say I actually did want something more specific. So let's say I just wanted the long arm of chromosome 10, right? So I can effectively grab this whole region once it loads. Right, so now I effectively grabbed, and you can see it's highlighted up here, the long arm of chromosome 10. So I can just grab this location, right? So it's basically location 42 megabase through 135 megabase. So if I just grab this and copy, I can put this, instead of the entire chromosome 10, I can just put that part of chromosome 10. And so now if we were to design this array, it would effectively target all of chromosome 4 and just the long arm of chromosome 10. So if I hit next here, you can see that it's targeting all of 4, 1 through 191, and chromosome 10, it's just targeting that 42 megabase through 135 megabase. And you can see the probe spacing here decreased because we're targeting less of chromosome 10. But again, this is all a balancing act. So this is all for 180,000 probes. But if we were to change this to a 2 by 400,000, the probe spacing would be more. So let's go back for a second I'm gonna go back here. I'll just copy this. So I'm gonna change this to a 2 by 400K. Next. Right, and I'm gonna put in those same coordinates. For this one, I'm gonna put start at base pair 1. So it's basically the entire chromosome 4 and the entire chromosome 10. So then I can hit next. And so now you can see targeting both of these chromosomes, the average probe spacing is like 800 bases, right? So that means that every 800 bases on the entire chromosome, there'll be a probe. So that's obviously like much higher resolution, like much denser. But the offside is that you get to fit less samples on the array. So only 2 samples. So all of it is a balancing act of how dense you want it versus how many samples you want on the array. And so let's say this is what I wanted, and that I thought that was pretty good. That looks pretty good. I can hit begin probe selection, and then you just put in your email address. Right, so then it basically, it takes a little bit of time to do the probe selection. So what happens is I'm giving it a target region, and then Agilent has this massive library of probes for the entire human genome. So then it basically sends what I want out to their supercomputers, and it says, based on these targets, pick all of the probes that would fit within those targets. So right now, what is happening on Agilent computers is it's basically trying to design that array based on the coordinates that I had given it. And so what I've done previously, so I'm going to go to this find designs. I can go to aCGH. So these are designs that I have created previously. And so you can see I did this chromosome 4 and 10 just yesterday or the day before to remember, right? So if I click this, then it gives me a little bit of metrics about, and so this is one that I had designed previously. This isn't the one that we just did, but it's effectively, it's targeting the exact same regions. So chromosome 10 and chromosome 4, this is a 4 by 180K. And so what it's saying is that in chromosome 10, it was able to cover 89.9% of the chromosome, and it put effectively 68,000 probes on there with an average probe spacing of 1,600. And chromosome 4, it covered 91% of the chromosome with 97,000 probes and an average of 1,600 probes for that. 1,600 base pairs per probe. Does that make sense so far?
Yes.
Okay. And so one thing that's nice is, let's say that this seems good for me. This probe spacing seems good, but if you really want to see, like, what does this look like on a gene level, or what does this look like in reality? So I can hit download here. Right, and then there's a lot of different things you can download, and this is based on that design, but I just want to download here the bed file, which is right here. Right, so I'm going to just download this bed file. Let's download it to my desktop. And I'll unzip it. Okay, so now that's on my desktop. So now what we can do is go back to UCSC, right? And I can go to HG19. And then I can go to my data, custom tracks. I'm just going to delete this that I was doing before. And so what I want to do is add a custom track. And so this is basically in UCSC, you can add a track to the genome browser. So what I'm going to do is I'm going to put in that bed file that we just downloaded. Where did it go? There it is. Okay, cool. So I am basically uploading that file that I had just gotten from Agilent. It's still uploading. Okay, so now I uploaded that file, and it basically says view in, and I'm going to hit genome browser, and I'm going to hit go. And so what this allows us to do is I'm going to go to chromosome 4. Oops. Right, so I went to chromosome 4, and so you can see this user track right here, right? And so this has a bunch, it basically looks like a black bar. But if I zoom in, so I'm going to zoom in maybe right here, just to a random spot on chromosome 4. Right, and then I can still see the black bar, but there's a little bit more gap. So I'm going to zoom in maybe to this region right here. And I'm just zooming into random parts. And so you can see the user track up here is basically what I supplied in. Each of these little dots is a probe. And so I can see physically where every single one of the probes for that array is. So I can see, let's say I wanted to make sure a gene was well covered. I can go in, and this is where all of the probes are actually sitting on chromosome 4. I can even zoom in a little closer, right? And you can see physically the probe itself is usually like 40 to 60 bases. Yeah, so it's like 60 bases. So that's one of the probes on this array. So that's a single probe, and I can even click it, and I can see exactly what that probe is and what the position of the probe is. And so if I zoom, let me zoom out 100 times. Right, so that's basically showing where all of these probes, I'm going to make that squish. Yeah, where every single one of the probe locations are. So normally when I design an array, like when I'm designing an array, I'll usually design it all and then I'll download that bed file and I'll put it into UCSC just to make sure that the region that I want to be covered is well covered. Right. And so if I go back to Agilent, Sure Design, right? So this design ID is basically what I would give Agilent to order this array, right? And you can see I've designed a bunch of different arrays in here for different projects, for MECP2, for Rabanal, for different chromosomes. So I think a lot of it is just like kind of playing around with the system to say how, because it's really an act of like, you want to be able to fit as much as you can on the array, but you want it to be a density that's useful for you. So I would say if you're trying to get exact breakpoints, I wouldn't go above like 2,000 bases average spacing. That's a good kind of cutoff for structural variance. If you're not sure, so the fact that you already have a good idea of where the translocation starts and ends, yours doesn't have to be as exploratory. But if you're not sure where a certain CNV starts and ends, you more likely want to try to cover the whole chromosome, just so that you have a better idea of where that duplication or deletion is actually starting.
Chris, what about like it's like a 4p10q? So just a short arm and a long arm of q10 is also enough for us now.
It totally would be, but you also have to think if you needed to use this again, right? And that's why I try to design it with the whole chromosome in mind for like reusability. So like even this one that I was just playing around with yesterday or the day before, this chromosome 4 and 10, this covers the entire chromosome arm. It's 4 by 180K, and the average probe spacing is 1600. So something like this would be perfectly fine for doing any type of like breakpoint or high resolution, but you can totally just cover certain chromosomal arms, and you can get that average spacing lower in general. And then so I think that is basically a good kind of primer for the use case that I think you guys would use this for. There are things that I probably won't go into now, but you can design certain, so if you want to be like very region specific, you can design what's called probe groups, which I can say, let me see this like 10 megabase region and make the probe spacing 100 bases. And you can design it as specific as you want. But I think for the case of what you guys are trying to do arrays for, it's more useful to do this kind of basic, let me go back to the aCGH, the standard experimental setup, where you can target chromosomal arms, you can target whole chromosomes, you can target specific regions. It's really just a choice of what design you want. I wouldn't do a 1 million. We just don't need to, unless there's like a very specific region. But typically, if we do a 1 million, we actually use, so I'm going to go back to this find designs. So these are all my designs, but there's also an Agilent catalog of things that they've already designed, which they have tons of different options here for. It's a lot of clinical things, but the one thing that we do use a lot of is the Agilent 1 million, which I don't see here. Yeah, this Agilent 1 million. So that's basically a 1 million array that covers the entire genome at a very high resolution. But I think for the most part, you guys would just design the array aCGH with a standard format here. But do you have any questions or?
Yes, like after the order and this order number, how it works, like are we gonna order in here or are we gonna do like forward this order to Margie?
So you would basically, I'll send you the email of our Agilent rep. So you would send that design ID. So it's basically this, you would send this ID right here to our Agilent rep, and you would say, this is a custom like 4 by 180K array. I would like to order 1 of these, or I would like to order 2 of these. And then they'll give you a quote with our Baylor discount. And from there, it goes to the Agilent manufacturing facility where they like print the array effectively. And that takes about 2-ish weeks to do.
2 weeks? Oh.
About 2 weeks to get the array. Yeah, so it's not the fastest process. So that is something to keep in mind.
Okay. Oh, I thought that
And it's
it's.
also the
Mm.
arrays themselves. I'm trying to remember the last price. Um, yeah, that's why it's like all of the arrays are the same price. And so you typically want to um, try to fit as many samples as you can on the array. So doing like an 8 by, if you have a bunch of samples, trying to fit your design on an 8 by is like much more efficient than doing a 2 by or a 4 by. So it's like all of it is just kind of like a game of how, let's see how much the array is.
But it's weird. Why all of them is the same price?
I mean, I think it's because it's like for them to either print one, it's like the cost of the chip itself. So I think it's like less necessarily like how much printing is done on the chip, um, as far as I understand. But it looks like the unit price the last time we ordered one, it's about $750 per chip.
Mm, yes, not cheap. Okay.
Not cheap. But if you were to say, and that's why I always try to like tell Jim, if I am going to order this array and it's an 8 by and I know I can strip it and use it twice, right? Then you can basically fit 16 samples on that $750 array. And so it's like 750 divided by 16, it's like becomes about $50 per sample. But that's only if you do a 16 by. The price changes if you do a higher resolution or if you don't strip it or if it doesn't work. So
Okay. Okay. No,
yeah.
unfortunately, we have just a 4 patient, not too much.
Yeah. So if you have 4 patients, again, you could do a 2 by and you could strip it, or you can do a 4 by and not strip it.
Okay. Okay.
I would probably recommend a 4 by if you have 4 patients to do.
Yes.
And then because then you can do it all in one shot, and then you can save that array, especially if it's like a chromosome 4 and chromosome 10, because I know that we have neither of those in the lab. So if anyone ever needs to check chromosome 4 or 10 again, you could say like, oh, don't, I already have this array, you just need to strip it.
Okay. Okay. That's it?
I think that's the general gist. So I think the first